Good day once again, everyone. All right, we're still on that Eastern Cape exam, right? Looking at work, energy, and power this time. So if you haven't subscribed, please just hit that subscribe button. All right, let's get right into it. They say to us we've got a crate of mass which is 50 kilograms that is at rest at point A. Now, please note, if I were you, as I read through the statement, I'm going to be filling in information. So I know this would have a velocity of 0 at A. Okay. They say which is at a vertical height of 5 meters above the horizontal surface. The inclined surface makes an angle of theta, right, with the horizontal as shown in the diagram. When the crate is released, it slides down the incline and reaches point B at the bottom of the incline with a speed of 8 meters per second, right? So I'm going to fill that in, right? So they say the incline exerts a constant frictional force of 72 newtons on the crate while it slides down. So we know that the value of friction there, so this would be kinetic friction. This would be 72 newtons, okay? Right, and now let's look at the question. They say state the work energy theorem in words. So remember, what does the work energy theorem states? It says the work done, okay, the net work done on an object is equal to the change in kinetic energy. Or you can say that work done by the net force will be equal to or is equal to the change in kinetic energy. All right, now let's go to the next question. They say use energy principles to calculate the angle theta. Right, now let's quickly have a look at what's happening in this scenario. Right, first of all, we don't have any applied force, right? And secondly, we know that we also don't have, we do have friction as it moves down the incline, right? So what I can do first is that, look, I've got the change in velocity, so I can find out the change in kinetic energy, but I also have the vertical height, right? So what that can enable me to do is to calculate, in this case, the work done by frictional force, right? So let's see. Let's say, well, the work done by non-conservative force. Now, guys, please remember, every time that I am, I've got a vertical height, I'll always run to this formula, right? So the work done by non-conservative forces will be equal to the change in kinetic energy plus the change in potential energy, right? So now, what are my non-conservative forces? For those of you who've watched my videos previously, did say non-conservative, work done by non-conservative forces, that would be work done by the applied force and work done by friction. But remember, we don't have an applied force, so this would be the work done by friction, right? And this would be equal to the change in kinetic energy. So this would be half m Vf squared minus Vi squared, okay, plus, so we've got mg, right, the height final minus the height initial, right? So this would be, let's try and just try and solve this. So we've got 50 kilograms, that's our mass, so that's half of 50 times our final velocity. This is at the bottom, right? This was 8 squared. Our initial one, 0 squared, right? Plus, again, we've got 50 times 9.8, right? Our final height, remember, we ended up at 0 height, but our initial height was at 5 meters, right? So please be careful when you are substituting there. Right, so let's try and get a value for that quickly. So this is 0.5 times 50, okay? Now, you'll agree with me, this is multiplied by 8 squared, okay? So we get a value there. Now, we've got 50 times 9.8 times a negative 5. So I'm going to actually say that gives us minus 50 times 9.8 times 5. Okay, so I've taken that 5. So I get there minus 850. So that would be the work done by friction, right? Now, please, I want you to note, guys. So what do I know in this case, right? We know that to calculate work done, right? Work done will be the force, right? So this would be frictional force multiplied by delta x, the cos of the angle theta. Now, what would be the angle theta? This would be the angle between the direction of motion. Where's this object going? It's going down the incline, right? And the angle, rather the force between, or rather the angle between the direction of motion and the force in question. So we know that frictional force is acting in the opposite direction, right? As the object goes down, friction is opposing, so the angle there should be 180, right? So this would be minus 850, right? We're given a frictional force. They said to us that's 72 newtons. So when I substitute here, I don't need to put in the sign, right? So this is multiplied by delta x, the cos of 180, right? This is minus 850. Okay, let me write it nicely. So this is minus 850. Right, so I'm going to look for delta x in this case, right? So cos of 180 is negative 1. So this will give me negative 72 delta x is equal to minus 850. So let's divide both sides by negative 72, okay? And I get a delta x value. Okay, so we're going to talk about that just now. So I've got minus 850. Okay, sorry. So that's negative 850 divided by negative 72. Okay, and I've got 11.81. Okay, so that's going to be 11.81 meters, right? Now, what have I done? I've found out what would be the displacement in this case of this object as it goes down the incline. So I found that displacement to be 11.81. Okay. Now we're looking for the angle theta. So how am I going to find that angle? Now remember, what do I have? I've got a value for the opposite side, which is 5 meters. And I've got the hypotenuse, which is 11.81. Can I not use my trig ratio there, which is the sine opposite over hypotenuse? So I can say, well, the sine of angle theta will be equal to opposite over hypotenuse, right? But what is my opposite side? That is 5 meters divided by 11.81. So remember, if I'm looking for the angle, I'm going to say, well, it's the arcsine of 5 over 11.81, right? Quite an interesting question, this. So to find that angle, so we're going to say shift the sign of 5 divided by 11.81, and I get a value of 25. Well, yeah, let's just say 25 degrees, right? So our angle will be 25 degrees. Okay, right. Nothing wrong if you decided to approach it using the work energy theorem, okay? In which case you would have actually found, the value of delta x as well, right? But of course you would have included, the component of friction in this case. Okay, the component of gravity, rather, Fg parallel, right? So now I think this would be the best approach. Right, so let's go to the next one. They say draw a free body diagram. They say after passing point B, the crate slides along a rough horizontal surface, right, coming to rest at point C, which is 10 meters away from point B. So I know that when I get to point C, my velocity will be 0, okay, because that is actually a rough horizontal surface, right? Now they say to us, draw a free body diagram of all forces acting on the crate while it slides from point B to C. Right, so now between point B to C, keep in mind that the crate was not, did not have an applied force. So I know it's moving to the right. So friction is opposing the motion. So this would be my frictional force. So that's friction force. Okay. But remember, gravity is always pulling this thing down. So this would be the force of gravity, or you can say the weight. Okay. But we also have the normal force that is acting on this guy. So this would be our normal force. So please remember that when you are labeling, please label in full words, right? So that we know what you are talking about. Okay, right. Now, the last question, they say to us, calculate the work done by the frictional force to bring the crate to rest. Okay, so now we know that, first of all, we know we've got friction there, right? But we want the work done by friction, okay? Now, remember that our box or whatever it is, a crate rather, slid from B to C, right? 10 meters. So it moved from 8 meters per second all the way up until it became 0. So we can say, well, actually the net work done is equal to the change in kinetic energy, right? Now, what was that change in kinetic energy? It's half the mass times final velocity squared minus initial velocity squared, right? So this would be half of 50 times our final velocity was 0, our initial velocity was 8, okay? So if we take that, okay, so now I want you to keep in mind, so we've got a half of 50, 0.5 times 50 times 0 squared, which is 0 minus 8 squared, okay? So that gives us negative 1,600 joules, right? Now remember, this is the work done. What are we looking for? They wanted the work done by the frictional force to bring the crate to rest. But remember, which forces are acting here, right? The net work done, it's only horizontally, that's only the frictional force that is acting, isn't it? So which means the net work done is actually the work done by frictional force. So which means the work done by frictional force in this case would be equal to 1,600 newtons. Okay, and remember, the negative is not necessarily telling us about direction, but it's telling us about a loss in energy. All right, and that is how the cookie crumbles on this question. I hope you guys really enjoyed it. Okay, I'll keep on giving you some content that is important, all right, as you prepare towards that final on Friday. See you guys next time. Sharp, sharp.